Yes.
Thank you. Okay, so it's my great pleasure to introduce you Emin Orhan today. So let me just briefly talk about his biography. So he did his PhD at Brain and Cognitive Sciences at University of Rochester. Then he did a couple of postdocs, one at Center for Neuroscience at New York University, another one on Department of Neuroscience at Baylor College of Medicine. And now he is doing another postdoc at Center of Data Science at, again, New York University. And basically, he has done a lot of interesting research, which brings together many different subjects, including machine learning, AI, cognitive science, and computational neuroscience. And today, he will talk us about his recent work, which was just presented last week at NEURS 2020, which brings together baby vision and self-supervised learning. Thank you again, Emin, and the stage is yours.
Yeah, thank you very much. Thanks for the invitation. Let me share my screen. Can you see my screen now?
Yes.
All right. Yeah, thanks again for the invitation. Yeah, I want to tell you about our recent work on self-supervised learning through the eyes of a child. And this is joint work with Vaibhav Gupta and Brendan Lake. Okay, so maybe I should. All right, so the basic motivation for this work is that is the observation that children start to develop a sort of sophisticated understanding of the world around them very early on in their development. And to give an example of this, I want to show you this sort of short clip of this baby.
This video shows me that how haptic is so important. As a person working in the area of haptics, without touching and exploring the subject, you wouldn't understand what's going on, I guess, right?
Yeah. This is. Yeah, so this was a sort of simple demonstration of a well-known phenomenon in developmental psychology called object permanence. So as you probably guessed, this is this idea that so all objects don't pop in or pop out of existence in the real world. And so this child doesn't seem to understand this idea when he is only 6 months old. Well, it's a little bit controversial, but what exactly they know or they don't know about this principle. But there's clearly a sort of something wrong about their understanding of this idea when early on. But then at around one year of age, he clearly sort of understands this idea. He doesn't seem to have any sort of problem with this idea, and so. And we're basically interested in understanding how this comes about, how this child sort of learns this seemingly non-trivial fact about the world. So one possibility is that maybe this is not very sort of difficult to learn, given the sensory experience that this child receives, and so he just sensory information, so he just sort of learns this principle through some generic learning mechanism. Or maybe another possibility is that this is actually this could be very tricky to learn, and so in that case the child would need sort of more substantive inductive biases, innate priors to learn a principle like this. And so, yeah, this is not a crazy idea. In fact, actually, a lot of developmental psychologists seem to believe something like this. This is a sort of famous paper from Liz Spelke, a famous developmental psychologist. So in this paper, she argues that what she calls initial knowledge, which includes things like this object permanence principle, are in fact innate. They're not learned. So of course this question is not a. I should also emphasize at this point that I gave object permanence as an example, but the talk will actually not be about the object permanence itself. But we can sort of ask the same kind of question for other cognitive and perceptual abilities of humans, right? So how do we come to acquire our cognitive and perceptual abilities? And you're probably aware that this is not a new question. This is a sort of an age-old question, and it's often known as the nature versus nurture question in the literature. And yeah, as I said, it's a very old question. And historically, the empiricist and rationalist traditions in philosophy and psychology give sort of diametrically opposite answers to this question. So on the empiricist side, people like John Locke, for example, emphasize the role of experience in shaping our cognitive abilities. So in this famous passage, for example, Locke likens the initial state of the mind to a white paper, a blank sheet of paper devoid of all characters. On the other hand, so rationalists like Leibniz, for example, emphasize the role of sort of innate capacities or dispositions in shaping our minds. Yeah, so in this passage, for example, Leibniz likens the initial state of the mind to a sort of block of vein marble, and what that means is that even though like there's no sort of apparent figure in the initial block of marble, the final form, the final figure is somehow inherent in it, and it can be sort of revealed pretty easily with some amount of sort of sculpting work. And this is a sort of very, especially for a psychologist, I think this is a sort of very modern way of thinking about the mind. Okay, so this was just to sort of emphasize that this is a sort of very an ancient question, and we're not the first to tackle this question. But the thing that I'd like to emphasize in this talk is that when you think this is a completely empirical question, and we can sort of address this question in a sort of completely empirical, experimental way. And to do that, we need basically two ingredients. And so first, we need to be able to characterize rigorously as possible the sensory experience that children are receiving during their development. Doing this sort of in its complete generality is not really feasible because it would require maybe something like a real world simulation of a child. And that's not really feasible, but we can sort of try to be as realistic as possible. And secondly, we need generic learning algorithms and architectures to determine what exactly we can learn from this kind of sensory data using these generic learning algorithms and architectures. So in this work, our goal is precisely to carry out this program in the visual domain, and again, because sort of addressing this question in a sort of general way is not very feasible. We're just going to focus on one particular aspect of this question, which is the development of high-level visual categories or concepts, and so. So then our motivating question is this question. So can we learn high-level visual concepts in this generic way, or does this require some sort of innate priors, innate biases that can't be learned by through these generic learning methods? So that's going to be our motivating question in this work. So I should mention, yeah, if you have any questions or comments, just feel free to jump in.
What do you mean by high-level visual concepts? Can you describe it for the case of like this baby, I guess? Like, what do you mean?
Yeah, so I guess these would be like everyday visual objects. For example, like, I don't know, chairs, tables, cars, like cat, dog. Yeah, these kinds of basic level visual categories.
Do you mean recognition of those objects? Like when you say learn is a very, I don't know. I think it's a very intense intense word. So do you mean like recognizing it, like, or do you mean like?
Yeah, so we need to somehow like, yeah, exactly. So we need to somehow like sort of operationalize this question, right? So so we're going to apply some of these like generic learning algorithms on this data, and then to evaluate whether we have learned high-level visual concepts. We're going to do like a bunch of different evaluations, but essentially you can think of it as recognition. Recognition is definitely one aspect of learning those high-level visual categories. I think maybe this is going to be a little bit more clear later on when we talk about the evaluations of the learned representations. But yeah, recognition is definitely like one big aspect of learning these high-level visual concepts. So let me next talk about the data set that we use for this purpose. So we used this SECAM data set. So this is a recent data set of longitudinal data set of headcam recordings from 3 young children, S, A, and Y, over a 2.5-year period during their early development. So we have 220 hours of video from one of the children, and roughly 140 hours of data from the other 2 children. And so the way this works is that so every week the child wears this headcam, and then they do usually a continuous 1 to 2 hour of recording. And then they do this roughly every week for over the course of this 2.5-year period. Right, so yeah, and then as I said, this sort of amounts to roughly 220 hours of video from one of the babies and 140 hours of video from the other two children. So the data set is audio-visual, so we also have the audio component as well, but in this work we only use the video component. But we're thinking about ways of incorporating the audio component in future work as well, in ongoing work actually. So, but in this work I'm going to tell you about today, we only use the video component. All right, so now, yeah, I just want to show you a sort of short clip from this data set just to give you a sense of what this data set looks like. Right, so this is just a sort of short example from this data set. Sorry. Yeah, and so as I said, our question is what exactly can we learn from this kind of data set using generic learning algorithms? And so to address this, we applied self-supervised learning algorithms to these headcam videos. After some trial and error, we came up with this very simple self-supervised learning objective that we call temporal classification. The basic idea in temporal classification is to divide the data set into these equal length segments or episodes, temporal episodes. And then the objective is, the task is to, given any frame, to tell which temporal episode or which segment that frame belongs to, right? So, and the sort of intuitive idea here is that, so when you think about the sort of high level versus low level visual variables in a scene, the low level visual variables are likely to change a lot from moment to moment. And so during an individual episode, they're not likely to be stable, whereas the more higher level variables, so for example, the semantic content of the scene, or maybe what the people in the scene are doing during an individual episodes, are likely to be more stable. And by learning to be invariant to sort of changes within an individual episode, we are hoping to learn those higher level variables within the scene. So that's basically the regularity that we're hoping to exploit in these videos. I want to make 2 points about this objective. The first one is that, so our motivating question is really about the sort of information content. So we're interested in understanding what can be extracted from this dataset in principle using basically any learning algorithm. So we're not sort of necessarily restricting ourselves to biological or psychologically plausible learning algorithms. Yeah, again, the question is like whether the information is there or whether the child needs like strong innate inductive biases in order to learn these high level visual concepts. But still, I'd like to argue that this objective is psychologically and biologically a plausible objective. Specifically, so there's this idea in computational neuroscience, going back to at least David Marr, where So it's sort of argued that hippocampus, for example, does this thing called the pattern separation. So pattern separation means that during sort of individual episodes in an animal's daily life, for example, the hippocampus gives each episode a distinct code, which is sparse and high dimensional and non-overlapping with other with codes for other temporal episodes. And these are sort of hypothesized to be useful for remembering that episode distinctly from other episodes. So even if two episodes are sort of similar to each other in the animal's daily life, they would still be remembered distinctly because of the sort of non-overlapping nature of these high-dimensional codes. And so in our case, these high-dimensional codes correspond to these class labels, right? So these episode labels. And because they are these one-hot vectors that indicate the temporal episode, yeah, and they also has sparse and non-overlapping because of this like one-hot nature of the those codes. So the second point that I'd like to make is that we're basically like using a very simple method to divide the entire video data set into these episodes. So we just take basically equal length segments in the data set. But I so strongly suspect that our method can likely be improved significantly if we use sort of more intelligent ways of dividing the data set into these episodes. So in particular, we can use sort of unsupervised event segmentation methods to come up with sort of better episodes that are sort of semantically more coherent. But I'm going to show you in our results that even using this like very simple idea of just dividing the entire data set into sort of equal length temporal episodes works very well for learning high level representations, visual representations. Okay, so yeah, that's our main self-supervised learning objective for learning useful high level representations, visual representations from the videos, headcam videos. Are there any questions about this objective, or is it clear? All right, so yeah, we also tried other self-supervised learning algorithms as well on this data set. So one, yeah, we in particular used contrastive learning objectives. So in contrastive learning, the idea is to learn to learn a representation of images, or in our case, video frames, with the property that so semantically similar images are mapped to similar locations in the representation space. So because this is self-supervised learning, we assume that we don't have access to like explicit semantic labels. And so in place of these semantic labels, what we do is we create sort of multiple copies of different sort of copies of the same image, applying certain transformations, and then treat those images as semantically similar images. So this picture shows an example. So we have this image of a dog, and then we apply some transformations to this image. So for example, on the left, maybe we apply a grayscale transform, and then we random crop. Do a random crop, and in the second one, we change the colors in the image. We apply color jitter, and then also apply a random crop. And because now these two images are generated from the same image, they share the same semantic content, right? And in contrastive learning, the idea is to sort of map these images to to the same location or to similar locations, and then to sort of repel the representations of these images from the representations of all other images, as shown here. This idea has proved very powerful in self-supervised learning from static images, and it's sort of close to state of the art on self-supervised learning from images. So one sort of weakness of this method for video is that it doesn't take into account the temporal structure in the video. So in video, the sort of nearby frames will be sort of temporally very correlated with each other, and so maybe it's not a very good idea to actually sort of try to repel them from each other, as this method will do, the image-based version will do. So we sort of came up with a sort of another version of this contrastive learning objective, where in addition to what you do typically in contrastive learning, you have a bias for mapping neighboring frames to similar locations, and so this sort of seemed like a natural, appropriate bias for video data, because, as I said, there are these temporal correlations between neighboring frames in video. So yeah, these are the self-supervised learning objectives we applied on our data set. And just to sort of foreshadow our results, the temporal classification idea worked better than either of these contrastive learning methods for our data set. We also have some baseline models. So these are basically like control models to make sure that sort of we're not fooling ourselves, right? So one baseline model that we have is an Imagenet pre-trained model. So we used our architecture that we use. We take the architecture we use for the self-supervised learning models, and then we take the sort of Imagenet trained version of that architecture. This is a strong baseline for object recognition. So if we can learn representations that match or maybe even outperform this baseline, that's a sort of good indication that we're learning useful features. The second baseline is a random untrained network. So this is basically, again, the same architecture, but an untrained network. And this is basically a control for testing whether we need learning for these tasks, for the tasks that for the evaluation tasks that I'm going to talk about later. And the final one is a sort of non-neural network model. It's just a sort of shell of feature-based model called histogram of oriented gradients. The details are not very important, but this just know that this is a sort of shallow baseline. And this is a control for testing whether we need deep representations in order to do these tasks that I'll talk about later. Right, so these are our baseline models. Any questions so far? All right, so again, just to remind you that our the question that we're interested in is whether we can learn useful high-level visual representations using self-supervised learning objectives from the headcount data. And to evaluate this, we mainly used two data sets. One is a subset of the data from the headcount data from one of the children. So this subset comes with some annotations, and using these annotations, we built this labeled subset of a labeled data set of frames or images, roughly 60,000 frames coming from 26 different classes. yeah, these are basically sort of everyday objects, visual objects that the child may encounter during their daily life. So these are things like I don't know, basic level categories like hand, table, door, computer, cat, car, chair, crib, things like that. And so on the left here, you see some examples of images from 4 different classes in this labeled dataset. And on the right is a histogram of the number of frames from each of the 26 classes in this dataset. So this is the first dataset that we use for evaluating our learned representations. The second dataset that we use is a dataset called Toybox. So this is a dataset of toy objects from 12 different categories. And so each category has 30 different exemplars. So each row is a different class here, and you see sort of different exemplars in each row. And so each exemplar in this dataset undergoes 11 different transformations. And so these are things like translations of the object, different rotations in 3D of the object. There's a sort of zoom transformation, and there are some other transformations. So the reason that we chose this particular dataset is because it's so it's sort of behaviorally more relevant data set for a child. So because these are toy objects, and compared to something like Imagenet, for example, which is a very much more complex data set. So this is sort of behavioral more relevant for a child. The other reason is that, so because it has this sort of nested structure, so each category has a number of different exemplars, and each exemplar undergoes different transformations. It allows us to evaluate generalization along different dimensions, right? So, for example, we can hold out a subset of the exemplars and test whether whether our models can generalize to the held out novel exemplars, or we can hold out a subset of transformations and evaluate whether our model generalizes over new novel transformations that it hasn't seen before, which is a sort of useful property of this data set. But in the paper we have other sort of evaluations as well. So, for example, we also evaluate the learned features on Imagenet as well, for example. All right, so so for our basic evaluations, we use a very standard evaluation protocol that's sort of popular in machine learning. So what we do is we take our models that are trained on the headcam data using self-supervised methods, and then we freeze them during the evaluation, and then we just add a single layer of linear layer on top of these frozen features to learn the classes in this downstream task, right? So yeah, this is sort of illustrated on this schematic here. So, for example, for the labeled S data set, as I said, we have 26 classes. These would be like 26 classes, and then we, in one condition, we, for example, hold out half of the data, so we train this linear classifier on that subset, and then evaluate on the remaining subset of the labeled S data set. And now I'm going to sort of show you the accuracy on that held out subset of the labeled S data set using this linear evaluation protocol. Yeah, let's look at the accuracy of the temporal classification model first. So these are 3 temporal classification models trained on data from the individual children, so S, A, and Y. And the dashed line is the basically the chance performance. So because this is this data set is unbalanced, so there are different numbers of examples from each class. The appropriate baseline here is the majority. So this dashed line is then gives you the accuracy of the majority prediction. So in the data set, I think the toy class is the largest class, and so this then gives you the performance of the of a model that always predicts toy, and we're doing significantly better than that baseline, so which is good. Yeah, as I said, these temporal classification models outperform these contrastive MoCo-based models shown in green, and they even outperform the sort of strong ImageNet baseline shown in yellow here. So again, this is a sort of very good indication that we're sort of on the right track. And also the other control models, the random model and the shallow histogram of gradients models, gradients model, they don't perform well in this task. So they're sort of barely above chance, which suggests that we really need to learn deep representations in order to perform well in this task. So again, these are also good indicators that this is a sufficiently hard task, and our models are learning useful high-level representations in order to perform well in this task. Okay, so so one sort of potential concern about this particular dataset, though, or this particular condition, is that so because these images are taken from video data, there are temporal correlations between images. So, for example, this shows the first, I think, 36 images from from one of the classes in this dataset, namely the cat class, and you can see that like neighboring frames are pretty correlated with each other. Which is a little bit concerning because it means that maybe the model could sort of make use of relatively sort of shallow strategies, superficial strategies to perform to exploit these temporal correlations in the data. So the fact that these control models don't perform well on this data set suggests that it's probably not trivial to exploit these correlations, but still we want to be absolutely certain that the model isn't sort of exploiting sort of shallow strategies to perform well in this task. We came up with a sort of control condition with another condition that reduced these temporal correlations in the data. So what we do is we just sort of subsample this data set, and now you can see that the temporal correlations are largely sort of reduced in this temporally subsample version. And so if you look at the performance on this subsample version, we see that overall the qualitative pattern is pretty similar to the first condition. There's just a sort of slight overall decrease in performance, which is expected. But otherwise, the main results are basically the same as in the sort of, the IID split, random IID split. Yeah, which is a sort of, again, good signal that the models are not just learning sort of superficial surface level regularities to perform well in this task. Okay, any questions so far? All right.
So, Emin, I have a question about this
Yes.
Imagenet baseline. So here
Yeah.
you are freezing most of the layers, right?
Yeah.
Did you
Yeah.
also try to just maybe propagate the new class information to some mid layers as well? Because there is a domain shift between the images captured from these headcams and the images exist in the Imagenet data set, right?
Yeah, so I think the domain shift would be a problem for only one of these models here. So the yellow one here.
Exactly.
The other ones are all trained on the headcount data, so they're like trained and evaluated on the same data set. I haven't tried that, but yeah, I agree. That's a sort of another common evaluation is to instead of doing this thing, sometimes people would do would take a sort of small subset of the data and then fine tune the whole model instead of learning a single layer. That's a sort of another common evaluation method. The idea there is more like sort of evaluating sort of few shot learning. So if you have learned like generally like useful features, so if the features that you learn are sort of sort of generically useful features, then just like using just a few, maybe a handful of labeled examples from each class and fine-tuning the entire model should sort of suffice for doing well on the downstream task. That's another evaluation method, but yeah, we haven't really tried that on this data set at least. I did some of that on Imagenet, on like downstream Imagenet evaluation, but not for this data set. But yeah, I agree. That's in fact, that may that may be a better evaluation strategy than just using a linear evaluation. But the reason that we use this is a very common one. I think the most common one in machine learning. Yeah. Okay, so let me now switch to the toy box results. So we do this kind of thing again, the exact same thing, but now on this other data set, toy box data set. Now we have, again, two conditions here, evaluation conditions. So the first one is random IID, so similar to the random IID split in the first case. What we do in this case is evaluate generalization to different transformations of the same image or the same exemplar. So so in this condition, for example, we could have an image like this in our training set, and then in the test set we have an image like this that is a sort of slightly shifted version of the first one, and so we're evaluating whether our model can generalize from this image to this image. So in the performance in this condition. So it's basically similar to the first data set that I talked about, with the only difference that the Imagenet model now performs slightly better than the self-supervised learning models. So this could be because the Imagenet is sort of the Imagenet model learns sort of more general features. In the first case, as I said, as you mentioned, for the self-supervised models, there's no domain shift problem. So maybe that's one of the reasons that they perform better than the Imagenet model. But the Imagenet features could be sort of more general features than the features that we learned from the headcount data using the self-supervised models, so self-supervised objectives. Otherwise the sort of patterns is sort of similar to the patterns are similar to the previous ones. So in particular, the temporal classification models outperform the contrastive self-supervised learning objectives. So these control models also do not perform very well in this condition. The second condition that we considered for this data set is an exemplar split. So in this case, we split along the exemplar dimension. So in our training set, we have we use 90% of the exemplars in the training set in the data set for training, and then evaluate the model on the remaining 10% of the exemplars. This is a challenging split because we're essentially asking the model to do a few-shot generalization task. So the model is only seeing like a handful of exemplars, 27 exemplars from each class, and then it's asked to generalize to completely novel exemplars from the same class. So let's look at the results in this condition. There's a sort of, as I mentioned, this split is more challenging, and there's an overall decrease in accuracy. And the Imagenet model, Imagenet trained model performs the best. But so reassuringly, our self-supervised model still performs significantly above chance, and they also perform better than these control models. Again, suggesting that this task is sufficiently challenging, and also our models are learning sort of useful high-level representations. Right. So yeah. Let me see. I guess I'm running out of time. Maybe I'll skip this part. We have some results sort of looking into the effect of sort of different factors, experimental factors on the performance of our self-supervised models. And basically, in summary, maybe the most important one is this sort of episode length parameter. So this is, if you remember, this is the sort of duration of the individual episodes that we divide the dataset into. And what we find here is that there's a sort of optimal episode length around sort of roughly 5 minutes. And so if the episodes are sort of shorter than that, the performance decreases. And that's because we're dividing if the episodes are shorter than that, we're dividing the dataset into sort of very fine episodes. So we're making basically distinctions between episodes that are semantically not very different from each other. And if the episodes are longer than that, in that case, we're sort of integrating over too much detail. Right? So we're integrating over differences that are semantically meaningful. So, for example, if we divide it into, let's say, 10-minute long segments, then during that 10-minute duration, the scene will probably change. That's just too long for a sort of semantically coherent episode. Maybe like the people in the scene will move to a different room and will start to do something else. And so if you sort of integrate over those differences, that's just too much detail that we're integrating over. And there's a sort of middle ground around 5 minutes that works the best. All right, so okay, maybe I'll skip this part too. This is just to show some visualizations of the kinds of features that we're learning in these self-supervised models. And the basic idea here is that the take-home message that I wanted to give with these visualizations, that so if you just look at the sort of these visualizations, it's really hard to sort of figure out what the individual features are doing, what kind of sort of features in the image they're sensitive to. And that's that basically means that the individual features themselves do not carry a lot of sort of class level information. It's rather the sort of the distributed the class information is distributed among the features. So it's not a sort of very localized representation of the class information. That's basically the upshot of these videos, and we can sort of quantify that effect. Just quickly go over this maybe. It's sort of not very different from what happens when you, for example, do supervised training on Imagenet. So in that case too, the features that you learn in the sort of the embedding layer of your model will not sort of correspond one-to-one with the sort of semantic labels in Imagenet, right? So what happens rather is that that class information will be represented in a sort of more distributed fashion among those features. And this is just a way to quantify that what I just mentioned, and the results that we have from the headcount data is very similar to what you would get in Imagenet. Again, the upshot is that semantic class information is represented in a distributed way, not in sort of individual features in the model. And we just that being said, so what happens in Imagenet, if you think about it, for example, is that even though those individual features do not correspond one-to-one with the semantic labels in the semantic classes in the dataset, you can still express those classes as sort of linear combinations of the features that you have learned, right? So, and something like that happens in our models too. So even though the features that we learned do not correspond to one-to-one with the, for example, the labels in our evaluation sets, we can still express them in terms of linear combinations of those features. And this just shows sort of an example of this. So here we have we show these attention maps for linear combinations of the features corresponding to a particular class in the dataset. So for example, on the left, you'll see the example for cat. So let me play this. So you can see that the model is picking up the cat in the image, and it doesn't pick up anything else. So it's sort of reassuring that the sort of it is responding to the correct features in the image. And you can see that this is sort of something interesting happens here. So the cat is being blocked by this toy object, and then you can see that the activation in the activation map is lowered, which is the correct behavior for the model, because it means that the model is really sort of sensitive to the features of the cat itself rather than any sort of temporal correlations between neighboring frames. Yeah, and there's another cat in these videos, and the model can also like pick up that object as well. So it's sensitive to the other cat too. So it's not very sort of sensitive to, like, I don't know, individual features of a particular cat. Okay, maybe also just another example. So this is for the computer class, or laptop, I guess. All right, so okay, yeah. Again, the goal here was to sort of convince you that these models are learning the right features rather than sort of exploiting, possibly exploiting sort of superficial surface level features of the images to perform well in these tasks. Oops. So let me move on. Yeah, these are some more examples, but in the interest of time, I think I'll move on. There's some new results from these models suggesting that self-supervised training on our headcam data also improves the sort of shape bias of our models compared to, for example, an Imagenet trained model. So the Imagenet trained models tend to exploit the local texture information in the images very strongly. But humans are not really like that. So there's this recent, very influential paper that shows that humans are much more sort of shape biased in their classification judgments compared to these deep neural networks trained on ImageNet. And what we find is interesting is that, so if you take our headcount trained models, they sort of significantly improve the shape bias of these models. So these models tend to exploit texture information to a lesser extent than the ImageNet trained models, and they rely more heavily on shape instead. It's still not as shape biased as humans. So, for example, in a sort of controlled experiment, this paper shows that humans would be up to 95% shape bias, whereas our model, whereas this sort of the ImageNet trained model of the architecture type of architecture that we used in this work has roughly 20% shape-based decisions, and using our headcount trained model, we can increase this up to roughly 50%, but it's still not. It doesn't go all the way up to sort of human level shape bias. All right, so before wrapping up, I just want to sort of mention two main limitations of our work. So the first one is that even though this is a substantial amount of data that we have, it's still a small subset of what a child experiences during their early development. The data that we have roughly corresponds to 1 week of visual experience, and so scaling this up to, for example, something like 2 years would require 2 orders of magnitude more data. And so recent results in machine learning, for example, suggest that increases in data size on this scale could lead to very large qualitative improvements in our models. So that's something to keep in mind. The second one is that we ignore because this is just a video data set, we sort of ignore the embodied nature of, I think somebody mentioned this in the beginning of the talk, so the human development is embodied, right? So humans can sort of use their bodies to sort of select the sensory experiences that they receive. That presumably sort of generates this rich array of sensory motor inputs that probably help the child better factorize the sources of variation in their sensory experiences. Right? So, but we have to sort of ignore this important aspect of development because we just have this video data set. So modeling this could require something like actual simulation in a sort of realistic simulation engine. But I think it's a sort of very interesting question to consider what improvements we can get by taking this embodied nature of development into account. Okay, so I'm just going to wrap up. In this work, we show that powerful high-level visual representations emerge through self-supervised learning when applied to developmentally realistic, longitudinal, egocentric video dataset. These representations, so we evaluate these representations in downstream tasks in a thorough fashion, and we show that these representations enable high accuracy in non-trivial downstream categorization tasks that would be behaviorally relevant for a child. They can support invariance to natural transformations. So this is the toy box example, one of the toy box conditions that I showed, and they can also support generalization to unseen category exemplars. So this is the exemplar split in the toy box data set. We also propose a novel self-supervised learning objective that we call temporal classification for longitudinal video data. So one sort of important point to note here is that, and this was sort of one of the main things that I learned while working on this project, is that so these like new self-supervised learning algorithms that are developed for static images are not necessarily optimal for video data, especially for longitudinal video data. So our data set is sort of a little bit uncharacteristic of even standard video data set in computer vision, which are much shorter in duration. So I think developing better self-supervised learning objectives, self-supervised learning algorithms for these longitudinal video data sets is an important direction. So I'm currently working on training video models on this data set. So in this work, I only talked about these image-based models, but now I'm training video models to see, for example, how much intuitive physics we can learn in this generic way. So including things like the object permanence effect, object permanence principle I talked about at the beginning of my talk. And also maybe like things like sort of action concepts, right? So the sort of high-level visual representations that we were interested in this work are more visual object concepts, but can we learn some visual action concepts in this way too? So that's another interesting question that we're interested in. Another direction is, as I said, so this data set also contains audio data, or linguistic data. So analyzing that data and sort of trying to incorporate that with the visual input to learn sort of better semantic concepts is another interesting direction. And finally, maybe like the most important takeaway is that, so I think we live in very sort of exciting times because of this sort of technical progress in both recording technology and in machine learning algorithms, especially in unsupervised machine learning. We can sort of make real progress on these very ambitious and ancient questions like the nature and nurture question. All right, so that's all. This work was recently presented at NeurIPS, and our code and pre-trained models are on GitHub. That's all. So I'm happy to take any questions you might have. Thank you.
Mm-hmm. Thank you, Emin, for this interesting talk. Actually, I have a couple of questions, but let me first ask our audience. So you can either use the chat window or you can unmute yourselves and ask your question directly to Emin.
Can I ask a question?
Yeah.
Yes, sure.
Like, do you think why the momentum contrastive learning doesn't work like the temporal classification? Because like I have saw a study from the Daniel Yemins and James DiCarlo's labs, their collaboration, and they were using some kind of contrastive predictive coding and SimCLR, I guess. So that was working well, but I didn't understand why didn't, like they were using same data set, I guess, the SayCam, like it was working well. Do you think why the temporal classification works better?
Yeah, I think they're. Yeah, I know the paper that you're referring to. I think they're doing something more complicated than what we did in. I don't remember the exact details, but it wasn't just the sort of. They weren't just using sort of this frame-based or image-based MoCo model. I think intuitively the reason that it doesn't. Especially the image-based version doesn't really do well on the video data is because of this temporal structure in the data set, right? So because, yeah, as I said, in MoCo, what you do is you take like, even like very sort of nearby frames that are very similar because of the temporal correlation, and you sort of try to sort of pull them apart, which is not really the best thing to do, I think. So because those are very similar images and they sort of share semantic content. And that's my intuition about why the image-based version doesn't really do well. Yeah, in our experiments, even this like temporal version that for mapping neighboring frames to similar locations also didn't really work very well. But yeah, maybe there's a sort of way to make it work better. But I haven't been able to come up with that. Yeah, it's not trivial, I think, to make that idea work well for video data. But yeah, I think the Yemen's paper that you mentioned, yeah, that's a good question. And yeah, as I said, I think the model they're using is not very similar to the MoCo models that we're using. It's somehow more complicated, and as I said, I don't exactly remember the details, but they're, for example, using like video embeddings, I think, and it's a sort of two-stream kind of model, as far as I remember. Like they have both a sort of image embeddings, and then there's a sort of video embeddings. So it's a sort of considerably more complicated model than what we had in our paper. Yeah.
Yeah, thank you.
Okay, another question. Okay, then I can ask my questions. So when you show us these neural attention maps,
Yeah.
I just think of whether one should also mimic human attention while processing this visual data as well. Like, for example, consider a foveated vision where you see only the centers that the baby is basically focusing on in some more high resolution compared to the surroundings. So did you think about this, or does it make sense to include such kind of a data augmentation to the original visual stimuli?
Yeah, that's an interesting question. We again, like we ignore that aspect of sort of human visual system as well. Yeah, as you mentioned, there's a sort of very big difference between the resolution at the center of the visual field versus in the periphery in the human visual system. Yeah, I think that's a good. I think I seem to remember a paper that that had an attention mechanism like that, and they were. I think they were suggesting that it sort of improves generalization, maybe. I don't exactly remember, but it could be useful for either like as a sort of data augmentation method. But we haven't really tried it. Yeah, as you said, like the reason it could potentially be useful is because if the object is in the center of the visual field, it's sort of it's centered on the sort of highest resolution region, and then the background becomes sort of more blurry, and then that could sort of reduce the effect of, for example, like these Imagenet trained models are very sensitive to background, and that's probably not, if you're trying to learn a sort of object recognition model that is sensitive to objects, that's not a really good thing, because it's sort of exploiting this sort of superficial correlation between the object and the background. But this kind of mechanism could reduce that sort of background sensitivity, background reliance. So that would be one reason that could be a good idea. And I think in that paper they were showing something like that, essentially, like it sort of reduces this reliance on background cues. But yeah, as I said, we haven't incorporated something like that. I think that's an interesting suggestion. Yeah.
Okay, thank you. I mean, so if we don't have any question, I have another one. Basically, you mentioned that the data is actually audio-visual. So in this particular work, you work on the self-supervised setting. But if we think about this extra audio input, can we call this as a form of weak supervision? Then can you also, or would you be able to use these self-supervision methods? Because, like, for example, the parents may be just saying words about the objects that the baby is playing with. So I think in that sense, it just goes away from self-supervised learning. Maybe. I'm happy to hear your opinions.
Yeah, I think that's a good suggestion. So actually, like one of my colleagues in our lab is working on exactly this problem, like trying to make use of that audio data as a sort of form of weak supervision to learn better semantic features. But one problem is that the sort of correspondence between the visual input and the this linguistic input is not very strong. So that form of supervision is like really weak, because like when for example the parent is saying something, it's usually not actually very related to what happens in the scene at that point. So it's a little bit different than, for example, the audio-visual data sets that you can have in computer vision, where even though it's a sort of still a weak, it could be a weak form of supervision, you at least know that what the audio is saying is somehow related to or describes the scene in some way. I think that correspondence is much weaker in this data set, and that's a little bit of a problem for making use of it. But it's still like it probably still has some useful information. It's not, there's some sort of extractable information there, but I think it's sort of much weaker than what you would typically get in like a clean audiovisual computer vision data set, for example. That's my impression so far working on this data set.
Okay.
Can I ask another question as well?
Yes, sure.
Like this is a more general one rather than technical. Like you are using some optimal sampling rate and the sequence length, and like the main motivation, like at least one of the main motivation was about getting what is the natural and what is the nurtural. So giving the, like you explained why you are using some optimal sequence length, because in like if it is so much narrow, then you can get the similar semantics as different classes, which harms the model. So like this is some kind of innate knowledge we can take. So like we are giving some kind of supervision as well with the optimal selection.
Yeah, I think that's a as I said, so our main motivation is to like address the sort of information content question, whether the data itself contains enough information to extract these high-level visual features. And so we're sort of we're less concerned about like using a like a totally generic learning algorithm that's sort of devoid of any I don't know, like innate mechanisms or any that's sort of psychologically or plausibly similar to what the child would have access to. But that being said, I think the dependence on the episode length was not very like severe, so it would still work pretty well. I suspect, like if it's like I don't know, half the optimal length or maybe like twice the optimal length. But maybe like when the performance gets really worse is if you use like if you use like either much shorter or much larger episode lengths. But yeah, as I said, our sort of main motivation in this work is to address that information content question. So it's why we're sort of less worried about how you can like optimally set that episode parameter. That could be, I don't know, that could be innate, or that could be something that's also learned during learning. That can be sort of dynamically adjusted maybe. But yeah, again, we haven't really like considered that question in this work. But yeah, it's a good question, I think.
By the way, like, have you tried to combine the momentum contrastive learning, like the image one and the temporal one? Like, would it work?
Yeah, I haven't tried that, but how would it be different from like, you mean how do we combine the two again? So is it just like using a combination of the features in the two cases,
yeah,
or
like you can get the loss from both, and like I don't know, you can do it like 2-stage in one epoch, maybe like one iteration. Like, I think that they should be combined in some way. I'm not sure how technically, but I wanted to ask, have you tried?
yeah, we haven't tried that. But they're also trying to do like slightly different things. So I'm not sure if like combining them in the way that you described, for example, would work well. Because, for example, the image-based one, so if you consider like two neighboring frames, the image-based one is trying to repel those the representations for those frames, but the temporal one is trying to attract them toward each other. So those are sort of conflicting things, and I'm not sure if that would be a good idea, like to try to do like basically conflicting things in different iterations of your training algorithm, or like in your loss function. Yeah, there might be a better way to combine them, but or maybe like modify the temporal one to yeah, I haven't thought a lot about this question, so I don't know. But yeah, as I said, so trying to combine them in a sort of naive way would probably not work very well because of this like conflicting nature of the objectives, I think. That's my intuition.
Yeah, thank you.
Okay. So thank you again, Emin, for this really interesting talk. And if our